All right. Good morning, everyone. I'm going to get started here. Um, do a little bit of administrative stuff and move forward. um, I have moved my position out to the porch, which means hopefully we won't hear the dog in the kitchen anymore, or at the back door asking to go out. Though we might get some street traffic, not much, but some. Um, we'll see. As I say that, I look back and notice they haven't come taking the trash yet. So expect, like, right when I'm getting into lecturing, the trash will come, and you'll hear the trash truck very loudly in the background. Um, so if there's any problems with the audio, let me know. Um, I've already done 2 classes with it. It seems to be a good setup. I'm standing now, not sitting at a table, so I can project a little bit better. I don't have that whisper voice because I have the microphone really close towards me. I'm a camera short of having what I need. My webcam isn't clear enough to display calculators as I use them, so I can't do demos of calculators. So hopefully I'll have a camera coming at some point that will deal with that. And I haven't figured out how to get my phone to project onto this stream. So it is what it is. What it is. Should be wrapping up the exam for chapter 3. I've had some email questions. If you need anything, please email me. I have been putting examples up on the playlist based off of the questions coming in, and I will have updated homework on Pearson. I am, as the emails going through, focusing on Pearson and the playlist as a place for keeping things. Keeping a copy on the 4 sections of Blackboard I have is taking too much time, so I figured the YouTube playlist is a good archive of the lectures, and Pearson is where the homework, quizzes, and exams will be. I will have the last exam before the final exam schedule posted shortly. Looking probably end of next week, I'll open it up. We are kind of comfortably in the material for chapter 4 from our presentation thing. Now, I know this is asynchronous. I know people are at different places in this. That's why the due dates are out about a week from when we're talking, and the material is recorded so you can look back on it. And that's just the nature of the situation that we're in. All right. What we're talking about now, and we're really wrapping up in polynomials, is the idea of, and we're just going to start with and move through the ramifications of the fundamental theorem of algebra. So the fundamental theorem of algebra says, hey, you've got a polynomial f of x that is degree n. It's got some leading coefficient and a power, and it has at least one complex zero, and I will continue to say root, zero, or solution. They end up being similar things, and they lead to our idea of factoring. So, these distinct zeros or complex zeros that have a couple things that happen. What we can say, which isn't, it's a consequence of the fundamental theorem, is that a polynomial of degree n has n zeros including their multiplicity. multiplicity. So if I have and as an example, I have a degree 2 polynomial with that touches the axis. I'll draw it here. Let me do a drawing. So we'll go to our friend the parabola, since we've seen the parabola off and on. The parabola will be the thing we'll use the best here. We're going to have this parabola touch at 1. And so it has x equals 1 as a solution. It has one distinct complex 0. And this is complex because its imaginary part is 0. And this function has the root, though, of x minus 1 squared. This has a multiplicity of 2. And that parabola has this polynomial form, which we've seen from quadratics. So it has 2 solutions. The one is repeated twice. And so the fundamental theorem of algebra says whatever this leading power is, whatever your degree of your function is, this thing here, out front, you're going to get that many solutions if you count their multiplicities. And so all the tools we've been developing are a bag of tricks to work from. I've got a 6th degree polynomial. I need to find 6 solutions, or the function's going to be doing some things in different places. But one of the things that we need to pay attention to are these complex roots and what happens with complex roots. So the fundamental theorem of algebra says, hey, you've got n solutions, n possible solutions, but they can exist in different forms. I'm going to scroll down here. And the form you can get is you can have a completely real solution. So in its complex form, a plus bi, that means b equals 0. There is no imaginary part. Or in complex form, where a plus bi, b does not equal 0. In my PB dyslexia. PBs and Ds I'll flip all the time. There we go, complex form. So these complex solutions, or this ability for this to be complex, carries with it a side effect, though. Complex numbers do not show in the polynomial. So let me write our generic form of the polynomial that we've been doing through the whole chapter. There's my nth term to my nth power. I descend in powers. Until I get to the constant. Now, none of these a's, all of the a sub i's, are real numbers. There are no complex numbers in there. So if I have complex roots, something has to have happened to them. Right? And that's something we saw when we studied complex numbers, which was if I have a complex number times its complex conjugate, there were no imaginary parts in the answer. So something has to happen that all the imaginary parts vanish, because we don't have imaginary parts in our coefficients. The coefficients are all real numbers. And the thing that happens is the complex numbers come in pairs. And so this is the extension we're doing here, is our complex numbers are going to come in pairs. And the pair includes its conjugate. And we should have noticed this kind of ancillary in our quadratics. When we were doing quadratics, if we looked at the quadratic equation, if this part here was imaginary, I would get the complex conjugate because of the plus minus in the middle here. I would get some complex number. I would have the front part telling me what the real was, and then in the back part, due to the imaginary term coming out of the square root, telling me what the imaginary part was. And this entire complex number came in a pair. And being the plus minus generates this complex conjugate. So when we were looking at quadratics and imaginary solutions were coming out, we were getting complex conjugates. And so I think the book actually calls this a conjugate zero theorem. And it says, let me scroll down, scroll here. As the book wording it, if it has only real coefficients, so if f of x has real coefficients, and a plus bi is a 0, then a minus bi is also a 0. And this is saying that if I'm only going to have real numbers, I need to multiply it by its complex conjugate for us to see those real numbers. And that's this effect here taking place. This middle terms canceling out when it multiplies by the conjugate. And mathematicians have proved, kind of due to the symmetry and triangular relationships of how these roots work their way through, that this is true about nature, that we get a complex conjugate whenever we go into that imaginary plane. Whenever imaginary parts of the solution come out, the partner comes with it. It's the only way we can see a real result, something in the real number plane. But that proof isn't really needed for us right now. We just need to know this happens. That if we get an imaginary part, we get its complex conjugate. So let's look at how the conjugate goes through. So we can find all the zeros of a function if we know parts of the function. So let's look at the example the book has here. I'm going to scroll up here. Now we're going to use the complex conjugate theorem here. So I have a function with real coefficients. So I have f of x equals x to the fourth plus x cubed plus 2x squared plus x plus 1. And so all of these a sub i's, whatever the a's are, they're all real numbers. A lot of ones. 1, 1, 2, 1, 1. They're all positive. So Descartes' rule of signs would say, hey, there's no positive real roots in this, right? And we'll put all our rules together as we go through. But this problem's saying, hey, you know what? I'm going to give you one. I'm going to say one of the solutions, 1, 0, is x equals negative I. We know 1 is x equals negative I. Well, if we know 1 is equal to negative I, the conjugate theorem says, hey, you get its conjugate, which is x is equal to positive I. So So by having this one imaginary zero, I'm going to change color here, I think. I'll do this in a different color. Purple. So I am given x equals negative I for some reason or another, right? And you'll see as we do different tests, we find ways to get particular roots. Then I am given with the fact that these come in conjugate pairs, I get its complex conjugate, which I change the sign of the imaginary part. I change the sign of the imaginary part and I get the other zero that it's conjugate pair. Well, the best thing to do with this is look at our power. We have 4 as our degree of this polynomial. So this polynomial has a possibility of having 4 distinct roots. It's going to have 4 roots with some multiplicity behind them all. I have a conjugate pair here, so the best thing to do is to turn these into factors. So I'm going to add I to both sides of this, and I get x plus I as my one factor, and I'm going to subtract I from both sides of this, and I get x minus I as my other factor. And so I know I want to find a particular pair of root, 2 more roots, because I have 2 of them. So I need to find 2 more zeros, 2 more roots, 2 more solutions. And so I want to use these factors to help divide this out. So I'm going to multiply. I'm going to multiply these 2 factors. So x plus I times x minus I. So I get x squared for my first term. I get a positive I and a negative I. They're going to cancel each other out, right? Which we're hoping for because this is what conjugates do. That middle term goes away. And then I get the last term squared. And I squared, if we remember, is equal to negative 1. So this would be minus I squared, or x squared plus 1. So why am I building back up? Well, I now have all of the parts in a term, a factorable term. These factors are together, right? Let's think of this as like 3 times 2, and this was 18. If I wanted to find the other factors, I would multiply this together and divide into 18. Well, I've multiplied this together, and now, or not this being 18, this up here being the 18, right? And I want to find the other piece. I multiply these together and divide them into the 18. So I multiplied these 2 things together to get the larger chunk that they represent. I want to divide that chunk through here. So I'll set up my long division. And we'll have to scroll down for our long division. X squared plus 1 is going to divide into our initial polynomial. So before I start the long division here, I'm just going to review what we're doing and where this is taking us. So I had a 4th degree polynomial. And for some reason, I knew one of the roots was negative I. Because that has an imaginary part, for free, I get positive I as the other root. But I know this 4th degree polynomial should have 4 roots, depending on the multiplicity of each solution or each root. So I need to find 2 more. So I'm using the conjugate parity to take the one I start with, give me its conjugate, and I now have 2 roots. I multiply the factor of those roots together, and I get this chunk here. I'm going to divide the whole thing by this chunk so I can work on trying to find the other 2 roots, or to see if it's a repetition of roots. All right, so we're going to scroll up, and we're going to do this division. So I look at leading terms, And for x to the fourth divided by x squared, that's x squared. And I'm going to multiply this back through. So x squared times x squared is x to the fourth. And x squared times 1 is x squared. I change the signs, or subtract, I guess is what we want to call that thing of changing the signs. My x cubed comes down, and this becomes a positive x squared. Now I need a new leading term, which is x cubed. So x cubed divided by x squared is positive x. I multiply x through, I get x cubed plus x. Oh, let me bring these terms down too, so I have them here. Bring all my terms down. And so x times 1 is x. I change my signs. And I add. So this brings down x squared, and this brings down a positive 1. X squared into x squared goes once. I multiply. I get x squared plus 1. Change my signs. And I have a remainder of 0. But I expected to have a remainder of 0 because this x squared plus 1 was built from factors. All right, so a couple things I can note here is I have readapted my problem. And this is the warning. I think some of you, when I was talking into class and talking about getting your paper to be helpful for you, well, once we get into polynomials, we'll find that we'll have problems that can start filling up a page. This is definitely where we start seeing that with some of these fourth degree polynomials and the multiple steps we need to do to tear them apart. But I have taken this larger problem and put it into two factors. So I have x squared plus 1 is one factor, and x squared plus x plus 1. Now I know this is x plus I, x minus I. I need to find the factors of this. And I'll go back to repeating, we like breaking these things down into smaller parts. Well, this is quadratic, so I'm not even going to play with any other part of polynomials. I'm going to go right to, this as a equals 1, b equals 1, and c equals 1. So it's minus 1 plus or minus 1 minus 4 over 2. All right, because negative b plus or minus b squared minus 4ac divided by 2. So I get negative 1 plus or minus the square root of 3 I, because it's a negative 3, all over 2. And this has a real part of 1/2 and an imaginary part. So if I write this in my complex form, right, separate the fraction into its two terms. And so now I have all of my roots. I have plus or minus I as a solution, and I have negative 1/2 plus or minus root 3 over 2i. This tells me this function will never cross the x-axis. It only has imaginary results. And it has 4 distinct roots, so it should have 3 wobbles in it as it maps its way back through. So let's look at that. Let me get this up here. Let's see. X to the fourth plus x cubed plus 2x squared plus x plus 1. And let's flip over. Where did you go? There you go. And so this function looks like this. It's never touching the x-axis. There's no real roots. The only time we get real roots is when it touches here. And so it zooms off there. It's an even powered function. So it starts at positive infinity and goes off to positive infinity. So there is a chance it'll never cross the x-axis because it is even powered. The leading coefficient is positive. That's why it stays on the positive side. And it just turns around. Kind of a flat turnaround there. And so this polynomial won't give us any real solutions. But knowing one of the imaginary solutions, we can break down the other solutions. And so this is what helps us start finding roots, is this fundamental theorem of algebra, that the degree of the polynomial tells us about the solution space. And so here, we start with what we looked at here. Fourth degree polynomial, we knew one complex root. The complex theorem says, hey, you get its conjugate for free. And so we have two of the four roots. Our job was to find the other ones. And so I multiplied these together so that I only had real numbers, and I divided that chunk by the larger bit. And that helped me find this expression for the other bit. And because this is a second degree, we're going to go to what chapter 3 helped us with. We go to the quadratic formula, and now we have all of our answers right here in the corner. So let me get all of our answers. And that's the game we have. Now, things that are completely imaginary, and this is something that you find, I think I tried to mention it when I talk about complex numbers, and it was one of the things mathematically, what does the imaginary number do? And it kind of helps a function turn in the background without actually touching the real axis. But when we look at word problems or reality, and we're trying to map reality into place, imaginary numbers are useful. They pop up in electronics a lot. But the general rule of thumb is real numbers are real measurable things. Imaginary numbers are kind of the pattern influencing the polynomial or the equation. The imaginary number influences how it moves, how it turns, where its max and minimums are. But it doesn't give this point of touching the x-axis, which is something real, something tangible, something measurable for an x value. And so imaginary numbers kind of hide in the background of our functions. All right, so let's see here. I'm going to, let's look at a polynomial. I want to get all of our rules together and look at some of the messier polynomials we can see and what all the complex solutions could be, so that we can then start working on the applications of these things. Because we now have our bag of tricks, kind of all the little bits and pieces in it, and we want to kind of put them all together and be able to pull different polynomials out. So let's see. I think I'll do this one here, and I'll point out to the pieces. So I'm going to point out to the different rules we use when solving this problem. And I'm just going to say you start with the fundamental theorem. Fundamental theorem, which says, degree n, you'll have n zeros with multiplicity. Now, I know that's not how the book states it. It says at the most. But I kind of want you to, underneath the hood, the number of solutions do answer n. In fact, if you pull out all the factors and you look at the powers of all the factors, they add back up to n on the degree polynomial. I think that's what the math is trying to say. So I want to put it in that best visual form. So So you have the fundamental theorem. The next thing you tend to use is Descartes' rule of signs. Descartes. No, I am not in a Descartes spelling mood today. So we'll just say Descartes. Descartes' rule of signs. And it says f of x, the number of sign changes, is equal to, is at most the number of positive zeros. At most, and you count down by twos. Now, the reason you count down by twos is the conjugates in the background of the complex numbers are always taking two spaces in your possible answers. So when you look at Descartes' rule of signs, you and you say you get 3 sign variations, you're going to have 3 or 1 positive root. If you get 4 sign variations, you're going to have 4, 2, or 0, because you count by twos and you count down from the number that you have. And that's because if it's not that positive one that you have, it could be 2 complex numbers, because complex numbers come in twos. And I'll put that up as the next one. And then you look at f of negative x and the number of sign changes is at most the number of negative zeros. I'll just put neg for negative. Got to learn to abbreviate more, so I can confuse you all with your notes. I am doing a summary, though. Abbreviations are the best place for in summaries. So we look at the fundamental theorem. We say this is an nth degree polynomial. We use Descartes' rule of signs to figure out how many can be positive or negative. What we usually do at this point is we chart all possible solutions, all possible types of solutions. And so I'll look at complex, positive real, negative real, and any one row of these has to add up to n. And then we use the rational root theorem combined with the remainder theorem to find rational real roots. And so this is our mode of attack on these, is we try to figure out how many things we need, what type of things they might be, so that we can figure out where we are once we get things. And then we use the rational root theorem and remainder theorem to find rational roots. If there are not rational roots, right, the intermediate value theorem will find non-rational roots. And so this is all the little bits and pieces we put together. This is the pattern that we're going to use them in. We're going to pull them out and we're going to work on them this way. So these are the steps I'm going to use to look at these polynomials that I want to look at here and see if we can find all the roots for them. I usually don't ask beyond 4th degree. If I ask something like 5th or 6th degree, they're usually factor really quickly once you have one of the rational roots. That's just because this technique you need to know how to do on odd functions and you need to do on even functions. But because it takes a while, it's good practices on the cubic and the fourth powers, because that gives you an odd one that isn't as big. I don't say I don't ask. I might ask a fifth or sixth power, especially when dealing with complex roots. But again, I tend to make them things that are they have a clear pathway when they're that large. All right, so let's look at a polynomial, and I will zoom up so you're going to see a little bit of this going on. I'll try to stabilize it as I point to the rules here. I would have put these on the far left blackboard and pointed back to them in a blackboard situation, but this isn't a blackboard situation. So the polynomial I'm going to look at here is going to be x to the fourth plus 2x cubed plus x squared plus 8x minus 12. Excuse me. So the first thing I look at, rule number one, is what degree is the polynomial. And this is a fourth degree polynomial, because that's the highest power of x. Now, I am going to need 4 roots or 4 solutions. So if I look at Descartes' rule of signs and I look at the sign changes in the original function, so I start with the leading coefficient. It's positive, stays positive, stays positive, stays positive, changes negative. So there is 1 sign change. That means there is at most one positive real root. Well, if I count down by 2s, I get to -1. And I can't have a -1 of something. So this is actually telling me there is exactly 1 real root. I'm not going to have 3. I'm not going to have 2. I'm not going to have 0. There's exactly 1. Because I got 1, Descartes' rule of sign says there was 1 sign variation for the positive version of the function. There is 1 and only 1 positive real root. All right, let's look at the negative. So negative to the 4th power stays the same. Negative to an odd power changes the sign. Stays the same. Changes the sign. This is positive, so I change once, twice, 3 times. So there are 3 sign changes. So there are 3 or 1 negative real roots. Because I have to count down by 2s. At most, there are 3 negative real roots. Counting down by 2 says there's 3 or 1. Can't be 0 or 2. 3 or 1. And that counting down by 2 is because that there might be complex solutions hiding in the background. Well, let's scroll up here and let's see what I've done so far. So I use the fundamental theorem to find the degree of my polynomial and how many solutions I'm looking for. I've used Descartes' rule of signs to show me how many are going to be positive and how many not are going to be, might be positive, might be negative. In this case, it shows me exactly how many are positive because of the number that came out. Now I want to chart all possibilities. So this is a 4th degree polynomial that has exactly 1 positive root. So no matter what combination of positive or negatives, I'm always going to have 1 here. Right? There's exactly 1 real root. So whatever combination I have, there will be 1 real. And my negative can be 3 or 1. So I'll start with the smaller term. Complex numbers come in pairs, and this row needs to add up to 4 because that's my n. So for this to add up to 4, I could have 2 complex numbers. That's one possible set of solutions I can have. I have 2 possible roots with 1 real solution and one positive real solution and 1 negative real solution. All right. Now again, because of Descartes' rule of sign giving me 1 and exactly 1 positive real root, the other option I can have is this has the full 3, which means I have no imaginary solutions, no complex imaginary solutions. And this are the only 2 sets of answers I can get. The really, really nice thing about this is because I got 1 for Descartes' rule of signs, because I got 1 for the positive real roots, I am guaranteed a positive real root. So I'm hoping beyond hope that it happens to be a rational number. But if not, the intermediate value theorem can help me with that. So I'm going to focus on positive real numbers with, I'm going to come back up here, the rational root theorem and the remainder, or I guess that's test, right? Rational root test and remainder theorem to find the rational roots. So my leading coefficient, my a sub n is 1, and my a sub naught is negative 12. So a sub n equals 1, and the constant is negative 12. And so these are the things that make up my rational roots, my p's and q's, right? Remember, we got to mind our p's and q's to find our possible rational roots. And so what we want to do is we want to make the list of all factors of 1, well, that's not too bad, and all factors of 12, which also isn't too bad. And what we're going to be looking at is the 12 over the 1s, right? So we say this was our p's and this was our q's. So all my factors of a sub naught are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And all of my factors of a sub n are plus or minus 1. So I have 1, 2, 3, 4, 5, 6 numbers with their plus or minus. I have 12 things to choose from. But I am focusing only on positive because I know I should have 1 and only 1 positive. So knowing I'm guaranteed that because of Descartes' rule of sign helps me run this search a little more quickly. So our possible roots are going to be these numbers, right? Because p over q, it's everything over 1. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And so those are all the possible rational roots that could be answers to this. They're the things that we multiply to give me my constant coming out of this from the leading coefficient. So the remainder theorem will help us choose these. So I need to grab my initial polynomial. I'll rewrite it back down here, still in blue. f of x equals, where is this ugly thing on my paper here? Flip a page over, flip a page back. Where did it go? Ah, there it is. X to the fourth, coefficient of 1. X to the fourth, 2x cubed. There we go. X to the fourth plus 2x cubed plus x squared plus 8x minus 12. All right, so my remainder theorem says if I take a number and put it into the function, if the result is 0, then that is a root. So I want to start with all my positives. 1 to the fourth plus 2 times 1 cubed plus 1 squared plus 8 times 1 minus 12. So that's 1 plus 2 plus 1 plus 8 minus 12. 3, 4, 12, 0. So my first root, x equals 1. All right. I'm going to use synthetic division because I have an x equals 1. And I'm going to simplify this problem. I'm going to move from a 4th degree problem to a 3rd degree problem. I'm really hoping to get to a 2nd degree problem because that will let me use the quadratic formula. I have one of my real roots, so I have to find a negative root out of this. And what I'm hoping to do is to make a simpler function to use the remainder theorem on. Right? I don't want to be plugging 12 to the 4th in here, so I'm going to use a simpler function. So my coefficients are 1, 2, 1, 8, and negative 12. So I'll bring down my 1. I'll multiply. I'll add. And then I'll multiply. All right, so we're doing the multiplied by each term, adding across our lovely synthetic division. So I'll put in 3. I'll add. Do my last multiply. 12. I should get 0 because I knew this was a factor. And there's no remainder. So my new polynomial is x cubed plus 3x squared plus 4x plus 12. And if I were thinking of where it came from, this root here is equivalent to the factor of x minus 1. And if you want to check when you're reviewing your notes, this would be a good time to multiply this back through and see that you get to the x to the 4th polynomial. But for me now, this is the thing I want to use. And I have my positive root, so I need to find my negative root. Or my negative roots, right? There's 1 or 3 of them. 1 or 3 of them. So I'm going to use the remainder theorem on this now. And I'm going to rename it g of x just to distinguish it from the initial polynomial. Just to have 2 different names. Nothing special, no reason why I wanted to call it g. And I'm going to use these roots, 1, 2, 3, 4, 6, and 12, but I'm going to use their negatives. So negative 1 cubed plus 3, negative 1 squared, plus 4 times negative 1, plus 12. Right, and our remainder theorem, this is g of negative 1. Our remainder theorem is we're hoping this is 0. Well, negative 1 cubed is negative 1. Negative 1 squared is positive. So we get 2, negative 2, positive 10. So negative 1 is not a root using the remainder theorem. using the remainder theorem. Again, be happy with calculator for these things. Calculator makes the remainder theorem go relatively quickly and makes it a lot more useful. When I first did these, we had to do these calculations by hand, and the powers of 4 just can get annoying, especially with things like 12. 12 times 12 is 144, but then 12 times 12 times 12, right? And then in 12 times 12 times 12 times 12. All right, let's look at -2. Then we're just going to keep working through our possible roots. But I'm just going to use the calculator to give my result. So I'm going to put -2 in. So I'm going to put this in parentheses on the calculator, and I'm going to work the answer through as it comes through. So -2 cubed plus 3 times -2 squared plus 4 times -2 plus 12, and I get 8 for that. Now I will use an up arrow on my calculator, and I'll just go through and replace in my parentheses all my -2's with -3's. Hold on 1 second, guys. You can just set it there. Thank you so much. Sorry about that. A package just came. And I am on the porch. I did say that would be the weirdest thing about the porch. Hopefully it's my camera and I can start recording calculator stuff. Many apologies. This does become 0. So I now have my other root, x equals -3. So we now have 2 of the answers. In 2 steps, we've gotten 2 of the answers to this polynomial. We know x equals 1 and x equals -3. Now what I want to do is I'm going to use synthetic division with this and with this to get this to be quadratic. That way I can use the quadratic formula. So I'm going to take -3. I'm going to take my coefficients from g of x. So I get 1, 3, 4, 12. I'll bring down the 1. -3 times 1 is -3. That gives me a 0. -3 times 0 is 0. Bring down 4. -3 times 4 is -12, which gives me a 0. That means this last polynomial is x squared plus 4. And this is nice because I know that the only roots this can have, because the positive sign here and no x term, is imaginary. And so I'll say x squared plus 4 equals 0. X squared equals -4, or x equals plus or minus 2i. Right? And we made this quadratic. Whew! That's a blackboard full of stuff. I'm going to walk back through it all and see how all these pieces go together and where this is coming from and where it's going. So we start here. We have a 4th degree polynomial. I need 4 solutions. I'm going to use Descartes' rule of signs to tell me how many are positive, how many are possibly positive, and how many are possibly negative. So Descartes' rule of signs says there's definitely 1 positive real root, and there's 3 or 1 negative real roots. So I put this into a table of all the possibilities I can get, knowing that if I get imaginary results, they come in pairs or 2s. It's a guaranteed 1 positive real, and I'm either going to have 1 or 3 negative reals, which means I can have 2 imaginary or 0 imaginary. Each row has to add up to 4 because that's what the fundamental theorem of algebra is telling me. I've got to have 4 things determining the zeros or the roots here. So I use the rational root test using the constant and the leading coefficient to find the possible rational roots. I plug the positive ones because I know for sure there is exactly one positive. So as soon as I find it, I'm done. And I found my positive real root at 1. Now, I don't want to keep working with a 4th degree polynomial. So I have one thing it is divisible by. So I divide it by that one thing to make it a 3rd degree polynomial. And I named my 3rd degree polynomial g of x. Now, it can only have the roots from the rational root test up above. In fact, the only thing that tends to happen here is the leading coefficient becomes something else and you can throw away some possible roots. But in this case, or not the leading coefficient, the constant becomes something else. And you can throw away possible roots. But you never gain any more. So I have simplified my polynomial down a degree. So I use the remainder theorem again, and I work my way through the negative roots because I have found my only one positive root. And I find that -3 is another root. Instead of dealing with the 3rd degree polynomial, I use synthetic division, and I now have a quadratic. And this quadratic is in a form where I know it's going to be imaginary. Right? We should have seen these in our quadratics. It has no middle b term. So I'm looking at, if I look at it in quadratic formula terms, there's no b. So it's 0 plus or minus the square root of -16 over 2. Right? Plus or minus. Because that's my b is 0. 0 minus 4ac. A is 1, c is 4. -16. And that will give you the same thing here if you want to use the quadratic formula. And so our goal has always been to reduce these things down. And so all of my solutions for x, I have x equals -3, x equals 1, and x equals plus or minus 2i. And I have now found all 4 solutions. Only 2 of them cross the x-axis. And I'm going to put this one up here so we can see that on how it manifests itself. So what did we have here? We had x to the 4th plus 2x cubed. X to the 4th plus 2x cubed plus x squared plus 8x minus 12. And let's bring it over here. And so here's this function on our graph. We have the 2 real solutions, and the imaginary is kind of giving it an inflection point out here somewhere, right? Because it dimples instead of being a nice parabolic. The imaginaries are influencing it out here. But if this was part of a polynomial equation, I would have my solutions. And that's what we're working our way towards, is solving polynomial equations. So we now have a toolkit where any degree polynomial I can break down into linear or quadratic things. And I can state every time it crosses the x-axis. And as we did with quadratics, as we did with linears, that place where we cross the x-axis is a solution. So we now have a toolkit where we can deal with polynomial equations. We can do polynomials that solve things, that model things, and we can find the places where they give us answers. we can also describe them in more complete terms. And so what ends up happening is real life data. The models we like to use tend to be quadratic because it has a clear minimum or maximum. But when we have complex data points, we will get large polynomial solutions coming out of them, large polynomials with different coefficients. And we will tend to use that model from the data to predict future behavior. And so we will want to set things where we can find where they turn to zero. And so we're going to kind of look at the idea of polynomial equations. And I kind of want to work on the intermediate value theorem a little bit more. We covered it very lightly on how we would find rounding. And let's look at a polynomial equation, and I'll move into that because finding things that aren't perfect rational numbers are useful. There's some tricks we can get to get everything to be rational numbers, but knowing how to get our repeating decimals that aren't fractions, I'm sure to say not repeating decimals, but our pi's and our e's and these irrational numbers, square roots of 2 and square roots of 3, to come out will be helpful. So I'm going to clean up here because I filled up the blackboard. I'm going to highlight, because I don't think the book summarizes this really well, is that the fundamental theorem will tell you how many things you're going to be looking for. Descartes' rule of sign is going to tell you how many of those could be positive or could be negative. You put that together with the fundamental theorem and you'll be able to tell what types of roots you're looking for. And once you have what types of roots you're looking for, keep track of what you're doing. Right? When I knew there was only going to be one positive and exactly one, get that out of the way, because I don't have to use the remainder theorem on any other positive number once that's done. And always, whenever you find one root, divide your polynomial down. Divide your polynomial down, because as soon as you hit quadratic, the quadratic formula will help you, and you will be able to find your imaginaries there. Sorry about that. Because that's one of the things about working on the porch. So let's look at equations instead of polynomials themselves. Not a huge change here from what we're doing. So let me clear this out. Am I still on that graph? Let me get off the graph, back to the blackboard. Let me erase this. Let me put up the new one. There we go. All right, so in essence, if we have a polynomial f of x, polynomial equation is I give it some value. I'm looking for when the polynomial returns a very particular value. And so we can find factoring as a way of solving quadratic equations. We can find factoring as a way of solving these equations. What we can do is create a new polynomial out of it. So I'll just continue in alphabetical order. G of x is going to equal f of x minus c. And if f of x is minus c, then that whole thing is equal to 0. All right, if I subtract c from both sides, I get f of x minus c on the left-hand side. On the right-hand side, I get 0. And so we create a new polynomial equal to 0. So, for example, let me get a slightly better. Grab the wrong example. Does not have the constant I want. Let me put my example in orange red here. So I have 4x to the fourth minus 5x squared equals 9. I have some relationship, some model. So we're going to say the original function f of x is 4x to the fourth minus 5x squared, right? Some temperature model. I don't know. For me, temperatures, fourth power happens a lot. With temperatures, the way radiation works, fourth powers come out of it a lot. And this is some law of cooling. It's some model we have. And we're looking for whenever the answer is 9. So we're looking for when f of x equals 9. So we can look at the whole thing, 4x to the fourth, 5x squared equals 9. Well, I can subtract 9 from both sides and get it to equal to 0. Why do I want it equal to 0? Because when I factored, those roots and solutions were the places where the function equals 0. And so this thing on the left-hand side here now, this 4x g of x equals 4x to the fourth minus 5x squared minus 9. Well, the zeros are equivalent to the solutions of this equation. So we spent all this time factoring and looking for when our functions cross the x-axis, because if we can set our function equal to 0, that gives us a solution. And we go, well, but things don't always equal 0. And notice, this does not equal 0, it equals 9. But if I subtract that 9 from each side, I make a new thing, a slightly different function that equals 0. And this new thing is the function we solve. So that's why we spend so much time breaking down functions, looking for when they cross the x-axis, and why I use the words roots, zeros, factors, solutions. Because they become solutions to equations. And they're how these things can solve out. So this is the function we're looking at. Now, I'm going to use this one here to show you a trick. And this trick is very useful. Instead of going through all of Descartes' rule of signs, going through the fourth power and dividing this down 2 times to get it quadratic, I want to notice something here. Notice this is counting by 2's. In fact, it looks very, very similar. It looks amazingly similar to a quadratic, right? What's our quadratic? A x squared plus bx plus c equals 0. Right? I'm counting 2 times this. We're going to do a thing called substitution. And substitution. And I think this is always the best place to show substitution. All of mathematics is taking something you don't know what to do with and making it look like something you've done before. That sounds simple, but it's complex, right? We had 7 or 8 rules that we started out with, a plus b equals b plus a times b equals b times a plus the parentheses b plus c equals parentheses a plus b, right? Our commutative rules, our associative rules, our distribution rule, our identity, a plus 0 equals a times 1 equals a, our inverses. And by manipulating all of those rules, we get everything else we've been doing. And one of our big things that we did was, a line crosses the x-axis somewhere, and we can solve for that. And so we've been breaking down our functions into their linear parts. But occasionally, we get things that don't cross the x-axis that matter, these imaginary things. So we needed to study quadratic things. And so with polynomials, we've been breaking them down to lines and quadratics so that they can pull apart. And so this idea of making harder problems look like a bunch of easier problems you've done before is really the tricks of mathematics. Each trick is a little bit different. Substitution is one of those. The thing about substitution in general is until you've done a whole bunch of substitutions, they're hard to see sometimes. And they can be a little bit confusing. But what I kind of look for is these are counting by twos or multiples of twos. Whatever this is times 2. Notice the power here is 1. 1 times 2 is 2. The power here is 2. 2 times 2 is 4. And so we say this is quadratic in form. It has the 3 terms. Whatever the middle power of the middle term is times 2 gives you the leading term. So it would be nice if I had another variable, our substitution variable. I'm going to do a bright green. And I want to change this by saying, hey, what if u equals x squared? I take another variable. I'm going to substitute with it. So if u equals x squared, then u squared is x squared squared. But my power rule says that's x to the 4th. Well, that's good because I have an x to the 4th here and an x squared here. So I can rewrite this whole thing in terms of u. So I'll get 4, it's my leading coefficient, x to the 4th. Well, x to the 4th is u squared. Minus 5 x squared. But x squared is u. Minus 9 equals 0. So what we're recognizing, and I'm going to go slow and overly emphasize things, might jump up and down a bit. If I had my chalkboard going, I might pound on the blackboard a bit, right, for overemphasis here. But this is quadratic in form. And we find the substitution that lets us write this as a quadratic. Which means I can now use my quadratic formula to find u. So I'm going to a equals 4, b equals negative 5, c equals negative 9. So u is equal to negative b plus or minus b squared minus 4ac over 2a. Right? So u is equal to negative 5 is 5 plus or minus negative 5 squared is 25 minus 4ac. So minus 4 times 4 is negative 16. Negative 16 times negative 9 is what, 144? Positive 144 over 2 times a, which is 8. So I get 5 plus or minus the square root of 169 over 8. Right, 25, 144, 169, yep. And I think the square root of 169, if I hopefully remember correctly, is 13. So I get 5 plus or minus 13 divided by 8. But those are my answers for u. And I wanted to know x, not u. So let's work out these answers. So if u equals x squared, let's put these in. So I'll give my two answers. 5 plus 13 is 18, and 18 divided by 8 is one of my answers, right? 5 plus 13 is 8. 5 minus 13 is negative 8. And so my two answers for u is 9/4. Whoops. Or negative 1. Double check me. I don't know, I'm double checking myself here, making sure that all of these add through. 5 plus 13 is 18. 18 divided by 8, that's right for the 2a. That's 9/4. 5 minus 13 is negative 8. Negative 8 over negative 8 is 1. All right, that works. But u is equal to x squared, and I want x. So x squared equals 9/4, and x squared equals negative 1. Notice I took the two u values I've got and I plugged them back into here. So this tells me x is equal. Somehow I seem to have gotten mine upside down. Oh, no, I'm in the right place. Yep. I take the square root of both sides and I'll get a plus or minus, right? When I take the square root of both sides, I get a plus or minus, and the square root of 9 is 3, and the square root of 4 is 2. Right? I'm taking the square root of both sides, I get plus or minus 3/2. Take the square root of both sides here, and I get plus or minus I. So, using the idea of an equation format, we can factor our functions. And we can find what x would be on our original equation. So this is why we do all this factoring, why we do all of this root finding. So my initial equation is this. I get the equation so it's equal to 0. That lets us treat the left-hand side as a function. And with functions, when they equal 0, those are the roots. They're the divisible parts of it. And I use this particular function to show the trick of quadratic in form. This is quadratic in form. And substitution is how we do that. Now, substitution will work. There are some things we'll do where we'll have odd powers, like let's see if I can scroll down here. Where this comes in really, really useful a lot of the times is x to the, let's see, let me see if I can remember one here. X plus x to the 1/2 plus 3. That's the same as if u equals x to the 1/2. Then this is u squared plus u plus 3. So the substitution will come in even when we're not dealing with polynomials. In fact, I think the book writes these equations as x plus the square root of x plus 3, which happens a lot. Square roots talk about distance to things. Square roots are ways of undoing a series of multiplications, right? We just did a square root in solving the u up above. So square roots will pop back into our equations. Substitution lets us find answers without having to work with the square root part initially. So this substitution is a nice thing to learn. And I think in this part, like the book shows this by going, hey, you can factor this. This is a factorable thing. You pull it apart and they use the tricks of factoring on it. Underneath that idea of factoring, I like to highlight substitution. It is the most useful. It is the only trick you have been using in algebra and mathematics. You have been substituting something else in for the problem you don't know what to do yet. And every little trick you have piled up is some form of substitution. We just pile up so many of them that they become these methods that we use for doing certain things. All right, I told you I was going to continue this week doing chapter 4 up to section 5. We have covered all the bags of tricks on how to solve equations, how to factor polynomials. There is one thing I'm going to start the next class with, which is section 4.4 in the book on the intermediate value theorem and estimating answers. How to estimate answers. Because the book only touches on this a little bit and it relies on technology. I'm going to show you how to do it a little bit by hand and the technology side by side. So it's going to take about a half hour, and that's a little more time than we have right now. And we're going to focus on the word problems that get us all the way up through section 4.5 in the book. So we'll be finishing 4.5 at the end of this week, and then finishing the rest of the chapter next week. Coming across, and then that'll leave us the last week of April and first 2 weeks of May to do chapter 5. And chapter 5 conceptually is a really tight nugget coming across. And you'll probably at the end of next week I'll do a little bit of function algebra. I will get the tests scheduled for chapter 4 up on Pearson. I will get a practice test similar to the practice test there. Please email me any questions you have on the homework. Please start digging through the homework on chapter 4. In fact, just email me anything you need, right? Don't sit there and avoid. Reach out. I am trying to, my email's getting quicker and quicker responses. So hopefully I should be turning around email a little more quickly on everyone. Yeah, I think I'm going to leave it on that. Be safe, be well. If you need anything, shout.